Okay, hi, I'm Roger. I'm Chief Architect at Esperanto, and we're going to split the talk in two pieces. Short intro on the vector instruction set definition from RISC-V. Very short. I'm the hardware guy. All difficult LLVM questions, please, to Robin. Just ask me easy hardware questions. So let's go quickly. In case somebody in the room has not heard about RISC-V, is a new open source ISA gaining a lot of momentum. And what people are attracted to it, if you talk to the people actually implementing things, are two things. Basically, open source, so no licenses, no going to ARM and paying a lot of money. And second, highly extensible. So very easy to say, I take the base, but I need 3 instructions for my market, and I'm just going to add those instructions. I know exactly how to do it. Let me go ahead and do it. So really popular. Probably you haven't seen lots of actual commercial designs yet. There's a lot of work going on in the shadows. It's happening. It's going to, blossom at once very soon. But there's a lot of work going on. And the ICE is actually very clean, very simple, and we're here because there's a backend in LLVM that Robin will talk about. So just a very quick, oops, I hit the wrong cable and this connector is flaky. There we go. So lots of big names behind RISC-V. Just this is a slide that the RISC-V Foundation tends to show, and you find your favorite company in the middle of this. So let's get down to it. So basically, the extension to RISC-V, so RISC-V has lots of fundamental base ISA plus a privilege ISA plus atomic extension, lots of small extensions that you can manage. We're going to talk about the vector one. And the idea really is that it can scale up and down to very large and very small cores. There's a public spec you can download from GitHub and do pull requests if there's something you don't like. So please come contribute if you feel like. And we got to version 0.7, relatively stable. Lots of changes in the MIG. If you've been following 0.6 and 0.7 were really different. 0.4 was yet very different, but it's now finally getting stable. And the goal is to have LLVM and others compilers, try it out, run, generate real code, give feedback to the working group that's defining the ISA, and from there, ratify it. We don't know when yet, but hopefully soon. Very high level, lots of support for easy vectorization. It does support mixed width computations, which is one of the major pains of all the old SIMD ISAs. If you know, I've worked many years at Intel, worked on AVX 512. You love pack, unpack, shuffle, permute. You know the long list of ugly operators we have there. So there was a goal here to clean that up. It does support fixed point floating 16. It does have precise exceptions, and a lot of open-minded towards extensions, right? So you can read, there are a lot of people, like in my particular case at Esperanto, we're doing our own extensions for machine learning as an example. Other people are doing similar things for other markets, right? And very important, the spec supports both a very classic old-style SIMD, whether you like it or not, you can build it if that's what you need, your market needs, or you can go to a very large temporal vectors. If you're old like me and remember Cray, Cray, when you started the vector operation, it ran for multiple clocks, right? It ran for many clocks. That the ISA does not tell you what to do, as opposed to other ISAs. You, as the implementer, decide how you want to do that, right? A lot of support for stream mining loops. A pain in other architectures I've worked on is the prologue and epilogue tend to be ugly if the code is big and you generate a prologue and an epilogue on a large loop, then the whole thing overflows the iCache, and then you get into trouble, and then you don't know what to do, and those things are gone. So very good support for stream mining. You'll just have one loop, no prologue, no epilogue, done. And that's thanks to active vector length. Masking on everything. So there was a very good I can't remember, but on that room, a very good talk by Simon on predication support in LLVM that goes right here. It obviously has strided lows, stores, scatters, and gathers. No surprise here. Reductions, and full parity with the scalar ISA. So everything you have on the scalar side, you have on the vector side. and then fault only first for loops with data-dependent exits. So you can say, well, do me a vector load, but stop on the first fault you hit. So that's gonna, well, the goal is to help the compilers generate, even on a while loop, if you don't know you're going past the array, you can still generate a vector load, fault on the first thing that falls, stop, and say, okay, did I do anything illegal here, or I just went past the end of my loop, so I gracefully just continue computing, right? What else? Let's get down to the actual architecture. Not many pictures. Hope you guys have good imagination. Basically, on top of the RISC-V ISA, it adds 32 vector registers called V0 through V31, super original naming. And each register is VLAN bits wide. And who chooses VLAN? You, the implementer. So each anyone implementing a RISC-V architecture with vector extension says, I want to do 128 bits, 512, 1,000 bits, 2,000 bits. Your decision, right? There's a bunch of restrictions on what you can do. It's got to be a power of 2. No funky stuff. But and then on top of that, there's a few control registers. Very important, VL, which is the active vector length, like in NEC and Cray style. SEW is a standard element width. We'll have a slide on that one, which helps say, okay, yes, I got 128 bits, but what's inside my vector? Do I have 8-bit things? Do I have 16-bit things? Or do I have 32-bit things? That definition is controlled by SEW. And then LMUL is the grouping multiplier. You can say, well, in reality, you know, I want to do a gigantic string copy, and I don't need 32 registers. I need 3 or 2. V0 and V1. Could you just make my vector register big? And that's what LMUL does. It says, sure, if you're willing to give up registers, so you're going to give up 16 registers, you'll get double length registers and things like that. Okay, maybe I got ahead of myself. SEW, you have a picture there and an example. Maybe we'll work backwards because you guys read faster than I can talk. The example below would be someone decided to build a vector extension with 256-bit, and at the particular instant we're looking at, the programmer set SEW to 32 bits, so then you would look at this vector register as containing 8 elements of 32 bits. How many elements? Well, VLAN divided by SEW tells you your maximum vector length, the number of things in your vector, and basically what's interesting is that you can set SEW as you also set your active VL. Robin will walk through examples, but there's an instruction set VL, and that thing underlined over there, E32, is saying, by the way, I want to set my VL now, and by the way, right now, I'm operating with element 32-bit objects. So everything in my vectors has to be considered as element 32, right? This capability basically saves a lot of encoding space and gives us almost, allow me to say almost, because with the room full of compiler people, if I say polymorphic, you'll kill me as I go out, but almost polymorphic, because many instructions actually just need to know fundamentally, am I integer, am I floating point, and then the size is contained in SEW. So we don't need vector add byte, vector add word, vector add double word, and that kind of ISA, right? Real quick, fundamental vector instruction, which I'm sure this audience fully understands, but a vector of floating point at, VV, vector times vector, of V0 is the destination, V1, V2 are the sources. The semantics is this for loop where you're going to go from the, take the elements in V1 and V2, add them one by one, and put the result in V0. Everything controlled by the active vector length, which is VL. And as you see in the picture, if VL in this example would be 5, only the first 5 elements of the computation are done. The other elements, the other 3 all the way to 8, are not done, and in this case are defined as 0, right? The interesting thing is that anything, we call these lanes, this would be an implementation with 8 lanes, past VL, do not raise traps, do not cause exceptions, nothing strange can happen with it, right? Let me talk about register grouping for a second. There's this feature where you can say, well, in reality, I want bigger vectors than I already have, and I don't need that many logical registers in my loop, can I group registers? And you actually can with LMOL. You can group them in pairs, in quads, or in octas. I don't know how you say that in English. And basically, let's say you set LMOL equals 2. Suddenly, you only have even registers. You have V0, you have V2, you have V4, you have V6, but you don't have V1, V3, and V5. Those disappear, and they get fused with the previous guy, right? So when LMOL is 2, we add 2, 4, 6 really means that V2 and V3 get the result of 4, 5 plus 6, 7, right? That gives more flexibility to the compiler. This trick is also used for widening. A difficult operation is, multiply 32 bits times 32 bits, you get technically a 64-bit object. The classical solution is mul high, mul low. Okay, kind of ugly. The solution in this ISA is no. Actually, we're going to use 2 registers at the destination. And I'll stop here and hand it over to Robin.
Thank you, Roger, so far. So, oh God. Okay, please hold on as I try to fix the connector. This one.
Just careful. It's very. Gotta give it. There you
go. Okay, thank you. Okay, I'm not touching it. Roger mentioned root mining, and that is the key to how you program this machine, actually, if you don't know how long the vectors are. So let's say you have a simple loop where you have a fixed quantity and you add it to every element of an array. You have the length of the array in A0, the pointer to the first element in A1, and the amount you want to add in A2. So you do a loop, and in each iteration of the loop, you tell the hardware, hey, I have this many elements to process. Just cap that at however many you can process in one, however many you can fit into your register. We also tell it these are 32-bit elements. So that influences how long our vectors are because it sets the SEW, as Roger showed you. And then we run this. This also sets the VL register, so the active vector length. So all these vector instructions, vload word, vadd, vstore word that you see there are then limited to that many elements. So, and at the end we did subtract how many elements we processed, we advanced the pointer to the element, and we see, do we still have anything left? So that leads to a pattern like this. Let's say we have a 10-element array, and we have space for 4 elements in our vector. Then the first 2 iterations we run with a full vector. VL is set to 4, to the maximum. And then at the end, when we run out of elements, when we would normally need a remainder loop, an epilogue, then the same loop runs, but with a shorter active vector length, and everything works out okay. We don't do anything. We don't do more iterations than we should. So that is the basic programmability. And the other part you have to, I want to show you how you program this machine is how you do mixed precision operations. Sorry, can you come in? Can you try again? Okay, so, right. The other part is mixed precision calculations. So usually when you have a loop with different data type widths, you just extend the smallest element width and your vector length is limited by the biggest element width because you want to fit it into one vector register like the 30-bit values here. That is fine, but it limits the throughput you have. So the alternative with RISC-V vectors is you pack everything tightly into the vector of the smaller element width, pack it into one vector. And for the bigger elements, you use a register pair, or if it's way bigger, a register quadruple, octuple, and use ELMO because the element, the arrows here show how the elements correspond, and that is exactly the mapping that larger ELMO values use and that widening operations use. So you can natively work with a vector that needs 2 or 4 or 8 registers to store because the elements are bigger. So you don't need to shuffle in the register, don't need these pack on instructions Roger mentioned. But of course it's a trade-off. You have fewer registers available and it's not a win on all microarchitectures, but it is an interesting alternative if you want to get the most out of your data path. So that covers the architecture, how do you actually program it. Now the question is, how do we generate that kind of code from LLVM? And I've been working on that out of tree here. I want to start upstreaming these patches to LLVM once the spec is frozen. As Roger said, it's a work in progress at the moment. It's not technically frozen or ratified, but it is getting stable. So far, I've mostly worked on machine code layer and code generation. I'm also interested in auto vectorization, of course, but that needs groundwork. And currently, you can write vector code in the R and code generate it. That looks a bit like this. I want to bore you with all the details. They wouldn't even fit all on the slide, but just this is the same loop as before in assembly, and it has the same loop structure. It's this VZVLI, VZVL intrinsic there, and we have this new vector type, scalable 1 times R32. And the rest of the loop structure is just regular arithmetic instructions, branches, like you know. So this R type, if you've been at a roundtable earlier today, you may have heard about this, or if you followed ARM SVE, they proposed the scalable vector type. And we, with RISC-V, have a lot of common ground with SVE. We'll have a vector register size that is fixed at runtime, but not known at compile time, and there's some known constant factor in that. So whatever gets accepted upstream for SVE, hopefully real soon, that will also work almost certainly for RISC-V. You can find the current proposal patch there at the URL. It's also, and that covers how to represent the vectors. And for the operations on them, we currently have target-specific intrinsics. This is an add, for example. And besides the 2 operands that we add together, there's also this VL argument and a mask. You didn't see the mask in the example earlier. There was no predication there, but in general, we need a mask. So this VL there is the active vector length that we use to do strip mining. And the masking is part of the intrinsic itself, not done externally. That is essentially what Simon Moll has been proposing with his vector predication patches as target-independent intrinsics. And you can find the patch there, and you may have been at Simon Moll's BOF talk earlier. The other thing to notice is SEW, and ELMU are not mentioned at the IR level. It's implicit in the vector types we use. So that covers the R presentation. To actually generate code, we need to figure out how to handle the vector length register and this configuration, so SEW and ELMU and some other bits. And for VL, we just use a normal allocatable integer register. It's separate from GPRs, but you can copy between them. It's an input to most vector instructions, output of VZVL instructions. And the configuration, the CSR, the register is called V-type in the spec, is a reserved physical register for LLVM. So it's implicitly used by most instructions. It's defined by VZVL instructions, and it's managed by the backend, not mentioned in the IR. However, the vector types you use in the IR indicate which element width and which length multiplier you should use in the backend. The backend should use. So during instruction selection, everything's straightforward. We just map the intrinsics that we've seen to instructions in the IR, to machine instructions. But we use pseudo instructions for different element widths and length multipliers, because our instructions are polymorphic, so to speak. So the same instructions can mean different things depending on SEW and ELMU. But we need to know which element width and which length multiplier we work on, for example, because a different length multiplier means that more registers are read and written. So for example, a scalable 4 times R32 add might be a pseudo instruction. We add element 32 multiplier 4. And at this stage, we don't insert the instruction to set that up yet. But we do that afterwards in a machine IR pass, figure out the right places. This is something I've not finished implementing yet because I'm still fighting ISIL bugs, but it's something that happens. I'm going to have to skip over other interesting bits on the slide because we're running actually 5 minutes. Okay, should be fine. So yeah, we have a couple of other tidbits like custom machine IR passes to optimize bad code that comes out of ISIL because of how VL is separate from GPRs, but nothing major. And copying vector registers is a bit of a mess right now because in general we need to copy the whole vector register. So we need to set the VL to maximum, copy the register, and then restore VL to the old value, and that's bad for code size, bad for performance, it copies too much data, and so on. In general, in most code, you don't want to copy the elements past VL because they don't matter. You're not actually using them. But in the backend, we have to actually go and prove in some way that these don't matter. So it's not quite yet clear how to do that. Maybe tweak the definition of the pseudo instruction in intrinsics. Maybe do an analysis of the uses of the copy. We'll have to see. So there's the current status roughly. Hopefully give you a bit of an overview. In the future, I hope to fill in more backend features because right now only enough of the architecture is covered to vectorize some loops and compile them down. There's lots more features in the architecture. And of course, we'll start looking at automatic vectorization and hopefully collaborate with the ARM SVE team again there because they have also similar needs of the auto vectorizer. We're going to see a software ecosystem start developing. We'll take a step back. There's going to be vendor-tuned libraries for common tasks. There's going to be hand-coded assembly kernels, but also maybe start looking at C-level intrinsics. And along the way, from the software, from the compiler side, and from the hardware implementations that are built right now, and those hopefully will start popping soon, we'll hopefully get feedback, maybe also from you guys, on the architecture, and maybe have to add a couple instructions, tweak some existing instructions, but hopefully not. So if this stuff interests you at all, please get in contact with me. There's lots of interesting backend work and IR work happening there. And yeah, so that's that. So we have seen this RISC-V vector architecture and flexible runtime configuration. We've seen a little bit about the backend I've started to build. And Roger says there's lots of industrial activity around it, even if you don't see it yet. So that concludes the talk. If you have any questions, thank you very much.
This is actually a question to you both, you and also the Graham back there. So what is your vision of like applying the TTI available vector register widths and also the interleaving factor on the scalable vector and the explicit vector representation here?
So there was some talk about interleaving at the round table about scalar vectors. I think you were present, but maybe you joined late.
Maybe I missed that one.
Oh yeah, you joined late. Okay, Graham can give you a better recap about that, I think. For the vectorization, for the TTI, I think my ideal vision would be to extend that hook to return a scalable size. So the vector type element count kind of deal. But perhaps we're going to have to move that from a number of bits to element type and elements and scalable flag, because that possibly matters once you start looking at scalable vectors. Does that make sense?
So I guess my vision of doing that is at least there is some unit of vectorization. Like in the case of ARM, I think it's 128 is a unit. And in your case, 64 may be the unit. Is that the case?
Yeah, it's a multiple of, depends on the specific target, triple, but 32 or 64 usually. But it's like not just the number of bits, but also how you partition them up, because like you wanna, the vectorization pattern you wanna generate something is maybe extending smaller element widths to larger element widths to make it match up. So at that point, it's not just about number of bits times something, but about the set of legal vector types in the backend, which becomes a bit more complicated when you have this length multiplier.
Okay, all right.
We can discuss details offline if you want.
Thank you.
Okay, any more questions? Okay, no question. Thanks again for the speaker.